Hello, beautiful people. Today we are going to look at Nypipe and Nypipe workflows. And to do this, I'm gonna walk you through a wonderful tutorial written by Michael Notter. And I cannot emphasize this enough. This tutorial is so good. I would barely say that it's the best thing since sliced bread. And you can find it online at Michael, and this is mykael.github.io/nypipe_tutorial. And this tutorial has a lot of topics in it, and we're only gonna cover one, which are workflows. And the whole tutorial is also neatly packaged in a Docker container. And the whole tutorial also runs inside a Jupyter notebook, so it's super easy to get going on your own machine, basically installing all of the software with Docker very, very easily. And this is what we are going to do today as well. So I'm going to click on Docker, which is a nice introduction to running this tutorial in Docker. I'm not going to go too much into details of this because this is not the main purpose of what we're going to do today. But this is where you can learn how to run it on your particular operating system. And well, I'm running it on Windows. So as you probably see, I already got Docker for Windows running. Yes, so this is already running. But this is not just Docker I need to run, I also have to run a specific Docker container. So what I'm going to do, I'm going to open PowerShell, which is basically bash of Windows. And I'm going to copy this command. I'm just going to modify it a little bit. I'm just going to remove this -v. You can read about it a bit more online, but that -v basically mounts a volume. We don't need that today for this very simple presentation. So I'm going to run this, and as you can see, it starts a Jupyter notebook. And to go and open my Jupyter notebook, I have to copy this URL. So I'm going to copy it, open the new window, and there we go. We're inside the Jupyter notebook server, and we can browse through all of the notebooks that Michael has created, and we helped with some of it that are designed to teach Nypipe. We're going to jump straight into workflows because workflows are probably the most exciting and important part of running Nypipe. Okay, so this is the Jupyter Notebook environment. Just a quick reminder here, everything lives in a node, and each of those, cell, in a cell. Each of those cells can be run, or in other words, executed, using Shift-Enter. So when I click Shift-Enter, I go to the next node and I run what's in the currently highlighted node. Before we will begin, we're gonna set up a few environment variables. Basically, those will help us later to visualize some of the nodes. Okay, so this is done. And for this tutorial, we're gonna do a very simple workflow where we're gonna scale strip an image to obtain the brain mask. And I'm gonna smooth the original image and mask the smoothed image. Okay, so if you live in a bash world, this is how you would do it. You basically would run bet on an anatomical image, and this is the anatomical image, and that will give you the brain or skull strip image with the mask image, and then you would smooth the image with a specified kernel, and then you would apply, or basically mask, the smoothed image with the brain mask and output that as a smooth masked image. Okay, so let's run this. So it's bad, so it's gonna run for a little bit. And here's, we can actually talk a little bit what's going on in the cell. So here, this percentage bash syntax enables running bash inside the cell instead of Python, which is the default. Okay, so this did run. So let's try to visualize the outputs of what we just did. So here we're gonna open a figure and we're gonna iterate over the 4 images: the original image, the smoothed image, and the masked image. So if we do this, we're gonna see that there is indeed the original image, and then it is smoothed, and then we can see the mask, and then after applying this mask to the smooth image, we have just smooth but masked image. Okay, simple. So now how can we do this in Nypipe? Okay, let's basically use the interfaces that are defined in Nypipe to do the same thing. So Nypipe basically wraps all sorts of different command line tools and MATLAB tools and other types of neuroimaging tools inside interfaces. And those interfaces can be run within Python to basically perform all of these procedures. So here in this piece of code, we're going to just start running just to speed things up. Alright, so let's have a look at this piece of code. Here, what we are seeing is that we have the FSL bet interface. So first we import FSL SAP package of Nypipe interfaces. Here we have FSL bet interface. It has an in file and out file. This file has to exist. This file is the file that we want. And this is the argument mask, which means that we should output the mask as well. And then we just run this thing. So we create an object which is an instance of FSL bet interface, and then we run it. We do the same with smooth, and FSL isotropic smooth has very similar input, and full width half maximum is this time in millimeters, and Nypipe will translate this for you, and again we can run it. The same with applying the mask. As you can see, we specified the same name for the output files as there are for the input files later, and at the end we can visualize, and it, lo and behold, does exactly the same thing. So do we gain anything from actually doing this way, other than we wrote probably like 4 times more lines of code? Well, there are little few things that actually add a little bit of sanity check to what we're doing. So for example, let's say we specify the name of this file, and and if we do that, it will tell us that this file does not exist. Okay, let me just so for some reason this does not want to comply with what I'm doing. Nonetheless, Nypipe does perform validation of input files and basically check whether they exist when we want to run them to begin with. And also translates the full width half maximum to specific sigma units that are expected by FSL. Now the question is, can we optimize this in any way? Yes, we can. So basically, if you imagine those two interfaces basically run one after another, you can access the outputs of those files. So basically, if I run this, you can see that now I assign the output of the run method to bet results. And this object will store all of the outputs, and I can access the output later. I did the same with smooth. So here, when I apply the mask, I set the in file, instead of setting it to the same string, like here, when I set it here, oh, well, that was the error. I actually was struggling before. So instead of setting it to the same output, I take it from this variable. And then we get exactly the same result. But let's dig into this a little bit. So look at bet results. It tells me that this is an interface results thing. If I look into outputs, I get a bunch of variables, and those variables I can reuse programmatically in the code, which I did over here. Okay, so I can connect things this way, but this is still not ideal because it's hard to programmatically to interrogate and figure out what are the dependencies. So in Nypipe, when we build workflows, we connect nodes together in a slightly different way. And it turns out that there is a problem on Stanford campus, which I bet all of you were dying to know. Nonetheless, carrying on, this is how workflows are actually built. So Nypipe has an explicit notion of a workflow, and I'm going to create one in a second. But before we create a workflow, we have to define nodes. So nodes are basically interfaces with unique names. So you're probably familiar with this notion, the FSL bet. We've done it before. Here we're just setting the in file coming from here. It's very important to use absolute path wherever you can. That will save you a few headaches. So this we're all familiar with. The new thing is that we put that interface into the node object. And this node over here, as you can see, it's imported here from the Nypipe module. We give it a unique name. And this name, well, it's unique in a way that in a single workflow you can only have one node with the same name. And this is important because those names are going to be used for working directory folders. So you basically can't have the same folders, two folders with the same name. And then we're going to use the same thing for smoothing. Again, we have a node. End file is the same end file. We give it a name. It's called smooth. And once again, node for mask. Give it the name mask. Okay, let's do this. And this is very quick because we haven't run anything. We just define the nodes that are going to be our building blocks, and we're going to connect them together in a second. But when we connect nodes, we don't connect them in some sort of vacuum. We connect them within a context of a workflow. So we have to create a workflow. Workflow has also a name. And once we have the workflow object, we can call the connect method of the workflow to connect different nodes with each other. And there are two different syntax ways of basically connecting nodes together. One of them is a bit shorter and simpler, where we basically say, I'm connecting node source and its output to node destination and its input. As you can see, the outputs and the inputs are strings. So those are string identifiers of those sockets. And source and destinations are instances of the node objects. So Python objects, strings, which are technically also objects, but we're not going to go into that. And there's a slightly more complex syntax where you basically build a list of connection, and a single connection is a tuple which consists of source node, destination node, and a list of socket identifiers that you connect. Output, input, output, input, output, input. Okay, so let's see how it works in practice. Here we call the method connect of our workflow, and we are connecting ScaleStrip and the socket mask file, which is the output of ScaleStrip, to the masking node and its input called mask file. And this will be with the simple syntax, and this is how it would look like with more complex syntax. Okay, so this is great. So we have our graph, we have our workflow. So the question is, can we see it? Can you view it? Yes, we can. So with this little syntax, the write graph function, you can write a graphical representation of your workflow, which, well, will be fairly straightforward because it's a very simple workflow. We have two nodes, smooth and ScaleStrip, which feed the third node mask, which will apply the mask from ScaleStrip to the smoothed image from smooth. We can also show a slightly more fancy graph describing all of this. And here we have the mask file, which is the name of the output of ScaleStrip that goes into the mask file, which is the input of the mask node. And we have the out file of the smooth that goes into the in file of mask. Okay, fairly straightforward. You can play around with those visualizations. There are more options to it, but let's just run this. Before we run it, we have to specify the working directory of the workflow. So this is where all the intermediate files will be stored, and we're gonna look into that in a second. But as soon as this is done, we can call run. And this is it. We just specified all the nodes and all the connections, and Nypipe will just figure out in which order they should be run and how the inputs and outputs should be passed along from one to another. As you can see in this growing log, that this is the bed running, and this is the smoothing running, and this is the application of the mask running. And this is great. It finished running, and we can try to visualize the outputs. As you can see, we're going to look inside the working directory. There you go. And those are the exactly same results that we looked at before. And we just achieved that with a simple workflow. Here's a fun advantage of many other advantages of Nypipe, where when I run this again, it will finish instantaneously because Nypipe caches all of those outputs and will check that none of the inputs change. So instead of running all of this again, it will basically collect the outputs and run this very quickly. Okay, so let's have a look inside the working directory. And inside it, we see that every node has its own, we call it sandbox folder. And inside it, you're going to have some provenance information such as the text file containing the command line, as well as the output. And you can learn a bit more how to play around with workflows by carrying on with this exercise on your own, as well as many others that are available at this wonderful tutorial made by Michael Notter. You can learn here, for example, how to input data from a bits dataset. You can also learn how to iterate over inputs using map nodes, as well as how to basically iterate over subjects using iterables, which is a very common thing to do. And finally, you can learn how to use data outputs where basically you want to select a few outputs of your working directory and store them with a particular name in a particular folder. So I encourage all of you to follow this wonderful tutorial, which has some real world examples with real data, and it's written in a very nice way. And which is probably most important, it runs from Docker, so it's very easy to start and it's very easy to follow. Before I finish, I would like to also show you one more thing, which is neurostars.org. So if you run into any problems and you have some sort of an error or you don't know how to do a particular thing, you can post a question on this forum. So this forum basically attracts different experts, and you can post questions about different neuroimaging problems, and here members of the community, including me and other Nypipe developers, will be very happy to help you. I also encourage you to check out whether your questions are already answered here. It usually suffices to take your error message and Google it, and you probably will be able to very quickly find your answer online. So this is all from me, and once again, all the kudos go to Michael Nutter for creating this tutorial, and I encourage you to check it out. And if you run into problems, go to neurostars.org and post your questions over there. All right, stay awesome.